Alright guys, welcome to this page of the notes. Now what we want to do here on this page is take a look at how you go about finding the determinant of a 3x3 matrix. And since the matrix is bigger, it is going to be a little bit more complicated than what we found with the 2x2 matrix. And actually there are two methods for finding the determinant of a 3x3 matrix, and these are them. You can do expansion by minors, or you can do the diagonal method. Now, we are going to do the diagonal method, all right? So this one right here is the one that we're going to use in this class. It's the one that I will show you and actually do example problems with. But I do want you to be aware of this expansion by minors method. It's a lot more popular normally when you get into college algebra or a linear equations class or something like that in college. They will ask you to do expansion by minors, and when you get there, I don't want expansion by minors. I don't want that to be the first time you've heard of it. Like, what the heck is going on here? Mr. Lawrence never showed us any of this stuff. I'm going to show you now. We're not going to do it because I like the diagonal method better, and I think you will as well. But I still want you to be aware of how the expansion by minors, or at least have heard of it, so that when you get to that college class and they say, hey, let's find the determinant by doing expansion by minors, you go, oh yeah, that's right, he told me this was coming. So here we go, this is how it works. What we're going to do in expansion by minors is this. We have a 3x3 square matrix. Now what you're going to do is you're going to take all of the elements in the top row. All right, so I'm going to take A, B, and C. All right, I'm going to separate those elements out. All right, so the first one I'm going to do is A. So there's my A. Whatever this element is, I just pull it down right here. Now because I'm using that element, because I'm using element A, I cannot use the other elements in the same row and column as A. So what that means is I don't use B and C, and I can't use D and G either, right? So what does that leave me with? Well, that leaves me with E, H, F, and I, which I will then make a 2x2 square matrix that I'll need to find the determinant of. The next element in the top row is B. I pull that one out. I'll explain to you in just a second why that B now needs to be negative, but you'll put a minus sign in front of the B, which means this. If B was a positive number, it would now be a negative number, and if B was a negative number, it would now be a positive number because you have a negative times a negative. Okay, but here's the point. Because I'm now using B, I can't use any of the elements in that row or that column, which means I can't use A and C. I eliminate E and H, and that leaves me with D, G, F, and I, which I will now use to construct a 2x2 square matrix that I find the determinant of. Finally, the last element in that top row, right, is C. So I pull the C out. It is now again positive. And because I'm using C, none of the elements from that row or that column can be used, which leaves me with D, E, G, and H, which I use to write a 2x2 square matrix. Now we just learned how to find the determinant of a 2x2 square matrix, so here's what happens. I have A times major diagonal minus the minor diagonal. Minus sign comes down with the B, right, because I had to make that number negative. Find the determinant of a 2x2 matrix, which is a D times I, and then G times H, and we subtract those. Then I have C, and again, 2x2 matrix, so I have D times H, and I have E times G, or minus E times G. Right, so again, if these were numbers, right, it actually works out pretty simply. We're turning a 3x3 matrix into a 2x2 matrix, right, which is much, much simpler to find the determinant of. So this method works perfectly well. You certainly can use it if you'd like to give it a shot, but again, you probably won't need to use it until, say, you get to college. Now, if you wanted to, you could just as easily use a different row. Let's say instead I wanted to use the second row. And here's the reason why you might want to use the second row. Remember I said that zeros, when we have zeros in our matrices, zeros are really our friend because it makes the calculations much simpler. What you would do if you did the expansion by minors method, you'd want to pick the row that has the most zeros in it, right? And here's the reason why. If E and F both happen to be zeros, right? Well, that means that this is 0, which times anything is 0, and this is 0, which times anything is 0, and those all go away, and you're just left having to do this guy, right? And it makes it much, much quicker to find the determinant of a 3 by 3 matrix if you can use whatever row has the most zeros in it. Now you're probably looking at this and recognizing the pattern that we used above. If I'm using D, that means I can't use A and G, and I can't use E and F, which leaves me with B, I, and CH, CH. But wait a second, up above, the A was positive, now my D is negative. I'll explain to you in a second how that works out. There's a system to that as well. But you should recognize that this is set up just like it was up here, except now you're just using row 2. And again, if you wanted to give this a shot on some of the example problems and see how it goes, please feel free to do so. Anyway, you wind up calculating your determinant down here. And now again, how do these signs work out? I've actually got that for you here on the next page. So flip over here to the next page, and this is the way it works. If you're using the top row, it'll be a positive, negative, positive. If you use the middle row, it'll be negative, positive, negative. And if you use the bottom row, it'll be positive, negative, positive, right? So you just use those signs if you did decide to do expansion by minors. But we're going to use the diagonal method, and here's how the diagonal method works. What you're going to do is you're going to take your 3 by 3 square matrix. Right? You're going to rewrite the first 2 columns. So A, D, G, A, D, G. Right? Rewrite it outside of the determinant symbol. Then my second column, B, E, H, rewrite it outside the determinant symbol next to the first column. So B, E, and H. That's the first step. Rewrite the first 2 columns. Now what you do, and this is why it's known as the diagonal method, you now run diagonally down through the matrices, multiplying all of the elements. So my first diagonal, A, E, and I, A times E times I. My next one would be B times F times G, B times F times G. My last one would be C times D times H, C times D times H. Add all of those together. We add them up. Okay? The next one, now I need to go the other direction. So G times E times C, there it is, that's my product. H times F times A, there's my product. And E times D times B, and there's my product. Again, add those guys up. Now, just as before, what's going to happen, right? You're going to do these guys. You're going to get a number down here, which I would call the bottom number. And you're going to do these guys, the other diagonal. The diagonal's going the other way, which you'll get up here, and you're going to get a top number. Well, just like with the 2 by 2 matrices, right? You take the major diagonal and you subtract the minor diagonal, and we said it's bottom minus top. Same thing here, right? These numbers I get down here in the red represent my bottom number. And I'm going to subtract from that these numbers here in blue, which represent my top number, right? So just like with the 2 by 2 matrices, it's going to be bottom minus top. That's a great way to remember. How do I do the subtraction? Because remember, the order of subtraction matters, and if you switch those, you're not going to get the right answer. So a good trick, just a nice way to remember, is always bottom minus the top number. So let's go ahead and give some of these a try. All right, here we go. I got this first one for us here. And again, remember the way that this works is the very first thing that you need to do is rewrite the first two columns. So I'm going to have a 0, a 2, and a 1. Rewriting the first column. Then I need to rewrite the second column. So 2, 3, and 2. Now, I'll use colors for this as well, just hopefully to help you keep track of it until you get the hang of it. My first diagonal is going to be 0 times 3 times 0, which of course is a 0. I'm going to add to that. 2 times 2 times 1 is going to be a 4. Oh, sorry, let me draw my arrow. Sorry, there we go. And then we're going to add to that 4, my final diagonal, 1 times 2 times 2, which again happens to be a 4. Now, I add all those guys together and we should get 8. I happen to have a blue marker here, so let's go ahead and do blue, going the other direction. So 1 times 3 times 1 gets me a 3. I'm going to add to that 2 times 2 times 0, which is a 0, plus 0 times 2 times 2, again, is 0. Add those guys up, and we wind up with a 3. Now, again, remember, in order to finish off this problem, you have to do the bottom minus the top. Bottom minus top, 8 minus 3. And the determinant for this 3 by 3 square matrix is 5. Hopefully that makes sense. Again, it's a process that you'll get used to. The reason I like this a little bit better than the doing the expansion by minors is just for this reason. With the expansion by minors, there's a lot of stuff to remember. First, you've got to remember that little matrix I showed you that had the signs, right? Positive, negative, positive, negative, positive, negative, positive, negative, positive, right? You'd have to remember all of that. Also, to do the expansion by minors, right, you've got to write, you have to determine, right, what's going to be the best row to use. Do I want to use the top row, the middle row, the bottom row? And again, that's not terribly tricky because of the zeros, but here you don't even have to worry about it, right? You just rewrite the first two columns and draw out your diagonals. And then after that, once you determine which row, then getting it set up correctly so that you have the correct 2 by 2 matrices. There's just a lot to remember, and again, with practice, I'm not saying that you wouldn't get good at it. I know that you guys would. Please feel free to give it a shot and see how it goes. You should get the exact same answer that we got here, and if you do, feel free to use it if you'd like to. I just think this one's a little simpler for you guys. It always works the exact same way, so I'll use this one. Let's go ahead and try another one. All right. Again, first thing we need to do is rewrite the first two columns. Rewrite the first two columns. So that's going to be a 3, a minus 1, a 0, a 1, a 2, 2, and a minus 2. Okay. All right. Now, I do the diagonals. All right, so it looks like my first diagonal. Sorry, this is actually this. I apologize. So your first diagonal is going to run right down through here. So 3 times 2 times 3. That should get me 18. Let's add to that my next diagonal, 1 times 4 times 0, which is going to be 0. We love those zeros. It makes it easy. Ooh, and I got another 0. 0 times the negative 1 times the negative 2, so plus 0, and we wind up with my bottom number being 18. Okay, let's go the other direction. Again, I'll change colors for you guys because hopefully it'll help you see it a little better. We go the opposite direction, so now 0 times 2 times 0. And then I've got negative 2 times 4 times 3. All right, well, so now I got something. It actually turns out to be a minus 24. So I'll add a negative 24. And then we're going to add to that. Looks like I'm going to get another negative number. Looks like I'm going to get a negative 3, right? Because 3 times a negative 1 times 1 would be a negative 1. So I've got 0, and I'm subtracting 24. and a negative 1, and I get minus 27. Well, remember, the way to finish this off is it's bottom minus top, so 18 minus, careful, watch your signs here, it's minus a minus 27. You'd have to add the opposite, and when you do that, I wind up with a 45. Fantastic, guys. Really good work here with the expansion, or I'm sorry, the diagonal method. Hopefully you like it. Hopefully you're getting the hang of it at this point. I have a few more on the next couple pages of the notes, so if you head on over there, we'll try this just until make sure that you're real comfortable with it. So head on over to the next page of the notes, and I'll meet you guys there.